Okay, let's get started, please. Any questions on what we're doing? Because it's not trivial stuff. Yeah, clear.
So when you do that homework problem that was about like you have a polynomial. Yeah. So the equation was like p of x equals px cubed plus. Hold on, it was basically to prove that there were
x cubed plus ax squared plus b. Yeah, and then cannot have three negative roots.
Yeah,
show that it cannot have three negative roots.
Run this by me again.
What?
Say one more time. P of x is
equals x cubed
x cubed
plus ax squared plus b.
And you need to show that it cannot have three negative roots.
cannot
Sorry.
have three negative roots. Okay, so roots, right? Roots are where the function is 0, right? So you can't have 3 points where the function crosses the x-axis to the left of the y-axis. Okay, that's what it's saying. Okay. Did it give you any hint about what you should do?
Use rules.
Use roles there. Okay. So the hint was use roles there. Use roles there. Was anyone able to figure this one out? Maya, great.
If you do Rolle's theorem and you solve, you get like one negative root and one positive root. And or like, sorry, not root, zero, like you know what you get two extrema, like a negative extrema and a positive extrema.
Okay, so
like if you derive
okay,
p
so,
and it's like equal to 0.
Okay, so let's look at consider p prime. Right, p prime is 3x squared plus 2x plus 0, right?
Yeah.
Right, so that's
if you solve for 0, you get like a negative root.
okay. Let's take a look here. So let's factor out, say, an x. Let's factor out, say, 3. Well, let's factor out an x first. Okay, so you get 3x plus 2a. Right. Okay, and so this thing p prime is 0 when x is 0 or x equals negative 2a over 3. Right? And did they give you that a was positive? Was a positive? Was it? Did they give you anything about a? No. No. Okay. So px equals 0. So these are the places where these are the possible places for maxes, right?
Yeah.
Or maxes and mins, yeah. And then what did you?
And like you would need two extrema, right, in the negative quadrants in order to have 3 roots.
You need, say it again?
You would need 2 extrema and like the kind of like the negative side of the graph in order to have 3 roots and 3 negative roots.
You would need to have 2 extrema on the left side in order to have 3 roots. Why is that? Why do you say that?
Because like in order to get a root, you have to like negative turn around, and like when you turn around, that's an extrema.
A root is just where you cross the line.
Yeah, but like in order to cross the line, you have like if you're going to cross the line in the first place, you have to like change direction in order to cross the line. That's right.
Okay, so you'd say, well,
Yeah.
so
Like right there's 2 negative roots.
okay. So you're saying that, well, if we had roots, then we would have extrema between these guys.
Yeah.
Okay.
Right.
Okay. Yeah. Yeah. Okay. Great. So you're saying, well, look, if we the only way we could have 3 negative roots would be if there were the only way we could have 3 negative roots would be if there were extrema between those guys. Right? Extrema between those guys. And that would mean that we have 2 strictly negative extrema. But here what it says is that there aren't 2 negative extrema. Right? At most there's 1. At most there's 1. Okay. So yeah, so that's good reasoning. Great, Kimaya. Yeah. Let me lay this out a little in a slightly different manner. So is it? I think the point to clarify is this one. Why is it true that if you have two roots, then you have a place where the derivative is 0 between it? If you have two roots, why are you guaranteed a place where the derivative is 0 between it?
Because for a continuous function, to cross over the x-axis twice, it has to turn, and at the turning point, the tangent line will have a slope.
Okay, so that's the intuition. The theorem that you want to cite. So what's the theorem that tells you this? Rolle's theorem, right? This is Rolle's theorem. Rolle's theorem says, if you're 0 here and you're 0 here, there must be a point where you have a zero slope in between, right? So let me lay this out in a sort of more orderly fashion. So Kimaya says, well, look. There are only two places where p prime is 0. Okay. If there were 3 negative roots, right? Then there would be. Let's call these 3 negative roots R1, R2, and R3. Just to put some names on them, right? So R1, R2, and R3. There's 3 places where you cross the line. Then there would be points. There would be 2 points. C1 in between R1 and R2, and C2 in between R2 and R3, where p prime of x is 0. Right? There would be 2 points where p prime is 0, and in fact there would be 2 negative points, right? Because they're between C1 and C2 are before R3, right? If we put them in order like this. Okay. Then there would be 2 negative numbers where p prime is 0, but in fact we say that there's only 1 negative number. At most 1 negative number where p prime is 0. Right? So you can't. So one there would be by Rolle's theorem. So one could not have 3 negative roots. One cannot have 3 negative roots. Okay, great. Yeah, Claire.
So would the zeros, like the roots, be the intervals for Rolle's theorem?
Yeah, you'd use these roots as the endpoints for Rolle's theorem.
Okay.
Right? Rolle's theorem would say, well, I'm guaranteed, I'm guaranteed a place where the derivative is 0 between these 2 guys, and I'm guaranteed a place where the derivative is 0 between these 2 guys. So I should have two roots of the derivative, right? 2 negative roots of the derivative, but we see that at most there's 1.
Right, and it's differentiable, because you can take the. Okay.
Because it's a polynomial.
Okay, and that will never be. That will never not exist. It will
right.
always be.
That's right.
Okay.
That's right. Because it's a polynomial. Polynomials you can differentiate.
Oh, okay, yeah.
Polynomials are differentiable functions.
Okay.
Everything. Okay. Anyone want to say anything more, or anyone want to ask questions about this? Good. Okay. Great. Okay. So, very good. Yeah. So I think people are getting sort of the sense, there has to be this turnaround, right? There has to be this turnaround. That you want to back up with Rolle's theorem. You want to say, because of Rolle's theorem, there's going to be this place where the slope is 0. To justify your intuition about this turning around. Okay. So so let's go back to the mean value theorem. Mean value theorem. As we said, many times the most important theorem in differential calculus. Can somebody tell me what the mean value theorem says? What does the mean value theorem say? Even if you can't tell me exactly what it says, can you tell me roughly what it says?
It says that at some point between points A and B, there's a place where f prime is the same as the slope between A.
Exactly. So under some conditions, right? So if blah blah blah, right? So if f is continuous and differentiable on the open interval. If it's continuous on this closed interval and open on this open interval, then there's a place inside where f prime equals f of b minus f of a over b minus a. Yeah, go ahead.
I'm sorry, I don't understand the distinction between it being on a closed interval but also on an open interval.
Yeah, so we're requiring that it be continuous on the closed interval. So it has to be continuous on the closed interval. If I said it has to be continuous on the open interval, then it could do something funny at the endpoints. It could jump at the endpoints, right? So we actually want it to be continuous on the whole interval, not the open interval, but the closed interval.
So why don't you just say it's continuous and differentiable on the closed interval?
Yeah, so the trouble is that when we talk about differentiability, we're talking about the limit of f of x plus h minus f of x over h as h goes to 0 from both sides, right? And so if our x is b, then we want to say the limit of f of b plus h. But the trouble is that there is no b plus h for h positive. There is no f of b plus h. The function is not defined out there. So we don't talk about differentiability at an endpoint because it sort of runs into trouble with the definitions.
Okay.
Yeah, like what does it mean f of b plus h? What's the slope of? There's nothing out there. Right. So we don't say differentiable on the closed interval because that would involve being differentiable at the endpoint, for which there's some trouble.
Okay.
It's true that you can actually sort of fix it to work by saying we're only going to talk about h going to 0 from the left-hand side, and from here we can talk about h going to 0 from the right-hand side. You can do these sort of one-sided derivatives, but to keep it simple, we're going to just stick with one derivative rather than left and right-sided derivatives. So you could sort of fix that up, but it's more trouble than it's worth.
Okay.
Okay, so this is the mean value theorem. And actually, so at the end of class last time, we sort of rushed through one exercise. And the exercise was this. If you have f and g that are continuous on AB, and differentiable on the interior, and say f of a equals g of a, f of b equals g of b, then you could say something. Okay, so I'm gonna put that back up. You have two guys, just to remind you. Oops. So they have the same beginning. They have the same values at the beginning, and they have the same values at the end. Okay. Right. And I don't know if anyone remembers. Then you could say something. We said something peculiar.
Oh, there's still a
Stefano.
point, right? Oh, sorry. I didn't look it up.
Actually, I'll just wait around and see if anyone else wants to talk. Does anyone other than Gwyneth and Stefano remember this? And Victor? And Megan? Okay, Stefano, go ahead.
They both have a point C where the derivative equals the average slope.
Okay, so are you saying that each of them has a point C?
Yeah, it's the same point.
And it's the same point. Okay, so that's that's something a little bit better than what the first sounded like. So yeah, so you could say, well, if we look at the mean, if we use the mean value theorem on each of them separately, then each of them has a point where the instantaneous slope equals the slope of this line, right? But in fact, we can say something better, which is there is some point where there is this, well, wait. So what do you say one more time, Stefano?
There's the same point C, like for both of them,
There's the same point C where what happens?
where they have the instantaneous velocities equal to the average slope of the line.
Okay. Okay. You know, I come to think of it, I probably said this wrong last time. So what you're saying is what I said, which was wrong last time. Yeah. But yeah, Victor.
Because then at a certain point, C, they both have the same instantaneous slope, but that's not necessarily the same as the slope of the line.
Yes. Yeah. So yeah, that's it. So there exists a point C where f prime of C equals g prime of C. So I think I said it wrong, and I said it both incorrectly and correctly last time. Right. So there's a point. If they both start off and end up at the same point on some linear track, then there must be some time where they have exactly the same velocity. There must be some time where they have exactly the
Is it
same
not the
velocity.
same time?
Hmm?
Is it the same time?
There must be some time, some point in time where they both have exactly the same velocity.
Okay.
But, oh, sorry.
Yeah, Gwyneth first.
But there's not are you saying that there's a point on the x-axis where if you looked up and checked both of them, they have the same slope?
Yes, exactly.
Really?
That's yes. It's kind of miraculous, right?
Yeah.
Yes.
Wait, and it wouldn't be the same as slope between the endpoints?
It's not necessarily. No, not necessarily.
Oh,
Yeah.
okay.
No, in fact, probably no.
See it, like, right on, like the.
We'll see it.
Sarah believes it.
Yeah.
People, yeah. So I always have people coming in after class. Well, what happens if you have a line that goes like this and a line that goes like this, and what they? Yes.
But they both still have a point that has the same slope as the secant line. They're just different. They can be different.
That's right. So
Okay.
the mean value theorem still holds, right?
Okay.
Each of them, you can say, oh look, this guy at this point, has the slope of the secant line. The other guy at this point has the slope of the secant line.
Okay.
That's true, right? That's true. You still have your points where the slope of each one individually equals the slope of the secant line.
Okay.
Okay. But this is what we're saying is something a little bit fancier, which is that there's some point where they have exactly the same slope. There's some time, and I don't see where it is. Maybe it's not here somewhere. So there's some time where there's some time where it happens. We're just going to pretend it's here. It's here. Okay. Yeah. Yeah.
Is this like a part of the mean value theorem, or does this have its own name?
Doesn't you could think of it as like something like the mean value theorem.
Okay.
Yeah. It doesn't have a name. It's just you could think of it as an extension of the mean value theorem. So there's the mean value theorem, but then you can sort of modify the mean value theorem. And this is maybe one easy modification. Does anyone remember? Oh yeah, Mariah, question.
I was going to ask, like, how do we find it?
Yeah, how do we know this? Does anyone? So, do you remember? So here's the thing. Remember how we proved the mean value theorem? Why was the mean value theorem true? Well, we took you had this one function f, and what you did was, why was the mean value theorem true? We used Rolle's theorem on.
Wasn't it like f is always the difference between the point or the line
and something else.
Yeah. So what we did was we said, well, look, consider the difference between f and this line. Right? Consider the difference between f and this line. By Rolle's theorem, there's a place where this equals 0. Right? Consider the proof of the value theorem. Recall was consider the difference. Rolle says that f prime minus L prime equals 0 somewhere. Right? F prime minus L prime equals 0 somewhere. In other words, f prime is the slope of the line somewhere. Well, that's the mean value. L is this line here.
Oh, okay.
Right? If we let L, we started off with f. There was no line. We said let's introduce a line. Let's introduce a line, L. Let's call it L, and let's consider the difference f minus L. Rolle's theorem says there's some point where that difference guy has a slope of 0. Right? There's some point where that difference guy has a slope of 0. In other words, f prime minus L prime equals 0. Right? F prime minus L prime equals 0. Right? Well, if f prime minus L prime equals 0 at some point, that means that f prime equals the slope of the line. But what's the slope of the line? Well, it's f of b minus f of a over b minus a. So we found the point. We found a point by considering the place where the difference equals 0. We find the point where f prime equals f of b minus f of a over b minus a. Anyone? Emma, is it making sense? Yeah. Okay. Great. Anyone? Yeah,
I
Mariah.
think this is kind of weird. This is in the extrema chapter.
What's that?
This doesn't tell you anything about like maxima or minima, right?
Doesn't seem like it.
Yeah.
Well, it doesn't seem like it.
Yeah.
Just wait.
Okay.
Just wait.
Just wait. I mean, you could rotate it, but like still.
Just wait. Okay. Just wait. Victor, yeah.
What's the derivative of d? Because it says d is equal to f minus L.
So d prime is going to be f prime minus L prime. Right. The difference, the derivative of a sum is the sum of the derivatives.
But does that number represent anything other than like I'm trying to make sense in what other circumstance would be useful other than knowing that whenever d prime is equal to 0 is when the slopes are the same.
What other circumstances would it be useful? Let's go back to this thing here. Okay. So let's just do exactly the same thing here. Right. Consider d equals f minus g. Consider d equals f minus g. Okay. So Rolle's theorem tell you. Rolle's theorem says. What? Rolle's theorem tells you nothing. What does Rolle's theorem tell you? You have a question? Yes. Okay. Yes.
So would that would no, it's from saying. In that case, would you call d prime the difference between the slopes of the difference between the slopes of f and L?
That's right.
Okay.
Yeah.
Okay, gotcha.
Okay. Yeah. So d is the difference between the functions. Right? D prime, because the slope of a difference is the difference of the slopes, is the difference of the slopes. Yeah. What does Rolle's theorem say, Kimaya?
That equals 0.
That equals 0 somewhere, right? So there exists a place where d prime equals 0, right? In other words, what? F prime minus d prime equals 0. In other words, f prime c equals d prime c. Right, so just apply Rolle's theorem to the difference again in this case, and you see that you find Rolle's theorem tells you this point where the slopes are equal. Okay. Where the second guy is not a line this time, but just anybody. Right? Anybody that is continuous on the closed interval and differentiable on the interior. Question? Somebody had a question? Yeah, right.
Okay, so there are 2 points where the slopes are equal to each other on like each function, and then there's 1 point where the slopes are equal to the slope between the endpoints. They're saying like 2 things about this, right?
No, so if we applied the mean value theorem separately to each one, we'd say there's 1 point where the slope, the instantaneous slope equals the slope of this line. There's another point, and it may not be the same one, where the slope, the instantaneous, the slope of the tangent line to the second function equals the slope of this secant line. But what we're saying here is something a bit better, which is that there's 1 point where the slopes of the tangent lines to these 2 functions are the same.
And, okay, yeah, and that's the slope to the endpoints.
It's not the
No,
slope
it's
of the
not
endpoints.
Okay, that's the other thing.
Yeah, it's not the slope of the endpoints, right? It's it's some you go like this. Let's see. So maybe there's it's the same thing. Okay, there's going to be some point around here, say, where the slopes of the tangent lines at the same point
Okay.
are the same. Okay,
Yeah.
but that's not necessarily
Yeah, it's not
the slope of the secant line.
Okay.
Okay. Oh my god. Okay. Okay. So yeah. Okay. So yeah, I was. If there was a lot more time, then I would say the next thing to do would be to see what happens if you have 2 functions that don't end at the same point. And this turns out to be something called the generalized mean value theorem of Cauchy, the mathematician Cauchy, which actually gives you a proof of the L'Hopital's rule. This is the justification for L'Hopital's rule, in fact, which some of you have heard of. Okay, so Stefano, help.
Yeah.
Do you have a question?
No.
Okay. Okay. So here's what we're going to use this for. So that we have the mean value theorem, right? Here are some corollaries of the mean value theorem, and these are pretty important. If f is differentiable on AB, so say f is differentiable on an open interval, if f prime is equal to 0 everywhere. When I write this triple equal sign, it means equal to 0 everywhere. So constantly equal to 0. Then f must be a constant. F in fact turns out to be a constant function. Okay. And then the second one, if capital F and capital G, why are they capitalized? I don't know. If F and G are differentiable, then on AB, if F prime and G prime are equal everywhere, then in fact F minus G is a constant. They differ by a constant.
And C be 0?
C could be 0, yeah. They might well be the same function, right? But
How would it not be the same?
you could have two functions that have exactly the same derivatives everywhere, but they differ by some constant. Okay. So okay. So in terms of like physical things, then maybe these are trivial statements, right? This is sort of saying if your instantaneous velocity is 0 all the time, then you are not moving. Right? Right. That's what this is saying. If your instantaneous velocity is 0 at every single point, then your position is constant. Okay, so that seems like a pretty obvious thing to say. Right? Second one, also equally obvious. If you have two cars and they have exactly the same instantaneous velocities at each point in time, then their positions must differ by a constant. Okay, you've got two cars, maybe one's starting ahead of the other, but they travel exactly the same speeds, right? Well, then the difference between their positions is going to be stable. Right?
So wherever it starts out, it stays the same.
Yeah, the difference will stay the same because they're going to travel exactly the same velocities. When one is going fast, the other is going fast. And when they're going backwards, you just. Okay. So these seem like they're pretty trivial statements. But I should say that functions are not cars, and you can have some pretty strange behavior with functions. I encourage you. I would explain it now, but we're already running out of time. I encourage you to look up something called the Cantor-Ternary function, which you can roughly say is velocity 0, 100% of the time, and it's a continuous function, but moves. So there's this car. It has a velocity of 0 100% of the time, but between time 0 and time 1, it moves from point 0 to point 1. Okay, so in any case, functions are not cars. Functions are not cars. The moral functions are not cars. And so one has to be a little bit careful. And let's just make sure that these statements are true, because there are some strange things that can happen. Okay. So So why? Why are these things true? Well, by the mean value theorem. Right. Mean value theorem. So here's the picture. Right. Here's A. Here is B. Okay. Let's do number 1. Number 1. So let's pick any 2 points. Let's call them A prime and B prime. Pick any 2 points, A prime and B prime. Here's AB, A prime, and B prime. Where A prime is the left guy. Okay. What does the mean value theorem tell you? Well, the mean value theorem tells you that there's going to be some point in the middle where
instantaneous velocity equals the average.
Mm-hmm.
Right.
So there exists a point between A prime and B prime where the instantaneous velocity equals f of b minus f of a over b minus a, with primes. F of b prime minus f of a prime over b prime minus a prime equals f prime of c. Okay. Mean value theorem says that.
I was asking why you're using primes.
Because I'm using these guys here.
Oh.
I'm applying the mean value theorem to this interval here. Okay. So I'm just picking two points in here, A prime and B prime, A prime and B prime, where A prime is less than B prime.
Okay.
Okay. And we're going to apply the mean value theorem there. The mean value theorem says that there's a place where the instantaneous velocity equals the slope between the two lines. But we've been given that the instantaneous velocity is always 0, right? So f of b prime minus f of a prime over b prime minus a prime equals 0. So what does that tell you?
I got that again.
We know that the derivative is 0 everywhere, right? We're doing number 1. If the derivative is 0 everywhere, then the function is flat, right? So here's the derivative is 0. So what does that tell you about f prime? What does that tell you about? What does that tell you?
F prime is.
Don't blurt it up. Don't blurt it up. Go ahead.
F prime is equal to F prime.
F of b prime is equal to f of a prime, right? Right. So we know that for those 2 points that we chose, they have exactly the same height. Right? But we could have done this for any 2 points. Right? We could have done this for any 2 points. So for example, let b prime move around. Well, f of b prime is going to be the same as f of a prime. Right? B prime is arbitrary. So f of x equals f of a prime for all, right, let me write this way. F of b prime equals f of a prime for all x in a b. Right? Just let b move around, you see that you always get that the slope of the secant line is going to be 0. Right? And so your function is constant. Right? So your function is constant. Okay. Is that clear? Any questions?
It's not just Rolle's theorem? Okay, never mind.
No.
Yeah, I guess. Okay.
No, because we don't know that these guys start off at the same height.
Okay.
All we know at the beginning is that the slope is 0.
Okay.
The instantaneous slope is 0. So this is sort of using the mean value theorem backwards,
Yeah.
right? Right. You could say we know the point where the instantaneous slope equals the slope of the tangent line, slope of the secant line, but we're doing it backwards. We're saying, what's the slope of the secant line? The slope of the secant line has to be f prime, but f prime is 0 everywhere, so the slope of every secant line here is going to be 0, and so the function is constant. Okay, so that's what we get, right? Slope of every secant line is 0. Okay. Okay. And then the second one, if you have 2 functions and they have exactly the same derivatives, then they must differ by a constant. Does anyone see why this is just almost the same thing as the first one? This is basically the same thing as the first one. Can anyone explain it? If you have 2 functions and they have exactly the same slope, then they must differ by a constant. Here's the trick. Consider the difference. Again, let's consider the difference. Right? What can you say about the slope of the difference? D prime is 0. Right? D prime is f prime minus g prime, but that's 0 everywhere. What does that tell you? That d prime is constant. Right? We just said if your slope is 0 everywhere, then you're constant. Right? So by part 1, d is constant. Right? D is constant by part 1, because part 1 said if you have a function whose slope is 0 everywhere, then you must be a constant. Look, we've created a function whose slope is 0 everywhere, so it's constant. Okay, so this sort of reasoning. Let me just throw in one thing here. suppose we knew that f prime was always bigger than 0. Suppose we knew that f prime was not equal to 0, but always bigger than 0. Then what would happen here? F prime is always bigger than 0. What would that tell you about f of b minus f of a over b minus a? Well, that's always going to be bigger than 0. What does it tell you about f of b minus f of a?
F of b must be bigger than A?
F of b must be bigger than f of a. Yeah. Yeah. So in other words, you have an increasing function. Right? Your function, if your derivative is positive, then f of b, whenever you have 2 points, the one on the right is going to be higher than the one on the left. Right? We'll talk about this more, but maybe this starts to lead into what does this have to do with maxes and mins? Right? Because if you know where the function's increasing, then maybe that tells you something. If you know where the function's increasing and where the function is decreasing, then that might give you some information about the max. Okay, but let me do the important example. So this is using number 2. So if f of x equals 2x and f of 1 equals 10, what is f of x? I'm sorry, if f prime x, equals 2x and f of 1 equals 10, what is f of x? Okay. So I'm just going to do this one because there isn't that much time. But here's how you go about it. You'd say, okay, I know f prime x equals 2x. Right? I know the derivative of, I don't know this function. All I know are its derivative and a value at a point. Okay. So I know what its derivative looks like. I also know that it passes through a particular point. Okay. Okay. So from here, I'm going to say, well, look, do I know any function whose derivative is 2x? X squared. Right? So I also know x squared has the same derivative. Right? X squared has the same derivative, right? That's good, right? Because from corollary number 2, what does that tell me? I've got 2 functions that have the same derivative, right? Same derivative as f. So what does that tell me about f? F must be, so f must be not constant, but f, the difference must be constant, right? The difference between f and g must be constant. So f must be g plus some constant, right? They have to differ by some constant, right? F must be x squared plus c for some constant. Okay, so that tells us that f has to be of this form, and then what is that c? You can figure it out from the other bit of information, right? We know that f of 1 is 10, right? So that tells us that 1 squared plus c is 10, so c must be 9. Right? Altogether, f must be x squared plus 9. That's the only thing it could be. Yeah, Mariah.
For more complex derivatives or longer ones, could there be many possible functions, or is there a easy way to figure out exactly if you're just given this information of point and the derivative?
Well,
what if it's really
you have something really complicated. Well, even so, the only functions that will have the same derivative are going to all differ by a constant.
Okay, yeah.
Right? They're all going to differ by a constant. So there's only going to be one, in fact. plus possibly different constants, right? Yeah, so that's a great point. That's a great point. You might think like, well, this is what people often think. They say, well, look, if I know this, I'm just going to guess this. I'm going to guess this. F of x is x squared plus 9, and it works. So I figured it out, right? But the point of this is rather that nothing else will work. The point is this, right? This is the only possible answer. This is the only possible. This is the significance of this is that there's no other function that'll work, right? Not just that this works, but that there's no other function that works. This is the one and only one answer, right? Because for f prime of x to be 2x, you know that f prime must be x squared, must differ from x squared by some constant, right? And then there's only one constant that works. So this is the only possible answer. You could go to your rooms and try and find some other function that works, but you'd never come out for the rest of your lives. Yes, Claire.
So there's no other function.
It's the ultimate timeout. Go to your room and find another function. that satisfies this equation.
So there's no other function that has the derivative of 2x.
Wait, what about 1/2 x to the fourth? No, never mind. Never mind. Sorry.
Well, the only other functions would be plus some constant. Would be x squared plus some constant.
Oh, because anything else would have an x.
Anything else, if it had the same derivative as this, it has to differ by this from x squared by a constant.
Okay. Thank you.
Okay. Okay, that's it for today.